Let's do this one. In this particular video, there are a few, MCQ questions here on angular momentum and angular impulse. So if you need to follow, read. The first one is this one. You have a solid disk of mass or radius r, and then mass m, and it rolls at a constant velocity horizontally here. And it wants us to just find the expression for angular momentum. So let's go ahead and do it. By definition, angular momentum is simply the moment of inertia times the angular velocity or angular speed, however you want to say it, if you consider direction. But you can break up I into 1/2 mr squared for this particular shape. The problem states that it's a solid disk, so the moment of inertia here is 1/2 mr squared. The problem gives capital M and capital R, so I'm just going to stick with capital M and capital R. And then omega is your angular velocity here. I don't know what that is. However, I can go ahead and substitute it out because omega is just V over R. Okay. So here, 1/2 mr squared just gets carried down. And as you can see, the 1/2 mr squared, the R is being square, while you have an R in the denominator in the second parentheses here. So the square and R square is going to cancel with one of the R's on the bottom here. So I'm going to go ahead and do that. So really, essentially, you have 1/2 mr times V. And if you want, you can clean up a little bit, or at this point, you can just look at the answer and know that it's B. But really, it's just 1 times M times R times V, which is just MVR. And then the denominator is 2. So we can just clean it up if you like. It would just be MRV divided by 2. And that is going to match answer choice B. Okay, so this one's pretty straightforward. The next one is this one. Here you have a dumbbell. They give you two scenarios. Again, if you need to read, but essentially here's the mass, the distance between the two dumbbells or the two masses here, and this dumbbell is known as D. And then they give a second scenario. The masses remain the same, except they increase the distance from D to 2D, and they kept omega the same as well. All right, so you're expected to find the relationship between L2 in terms of L1. So all I have to do is find L1. In the first diagram here, L1 is just I omega square. L1 is just I omega, not omega square. I'm not sure why I said that. But I do want to point out that these particular masses at the end of the dumbbell here is going to be treated as a point mass. So the generic function for I is just C mr square. So C for these 2 point masses, M is just going to be a 1. All right, so I'm just going to go ahead and substitute this out. The distance from the axis of rotation, this is where angular speed is given, or angular velocity here is given. The axis of rotation is right through the center of the system here. So you need to make sure you measure stuff correctly. So this distance here is just going to be D over 2. The whole schematic from M to M is D. So the distance from center to one end of the M is just half. So it'd be just D over 2. That's important because I'm just going to go ahead and do this one. Right? You have two masses. The mass of the rod is ignored because this is negligible. So here, I01 is just really M of the left times how far is it away from the axis of rotation, which is in the center. And that distance from the axis of rotation to where M is just D over 2. Make sure you put that in parentheses, square it. And then you would do the same step for the mass on the right. At this point, if you want, you could have just look at it and say symmetrically, there are 2. So really, you can just do 2 times MD square over 2 here. But I'm just going to write it in individual terms just so hopefully it's easier for you to follow. All right. Other than that, so inside the bracket, I have 2 of these because there are 2 masses. And I'm just going to clean it up. The exponent gets distributed to the D and the 2, so it'd be D squared over 4. Likewise with the second term here. And as you can see here, you have 2 identical terms. So really, it's just MD squared over 4 plus MD squared over 4. So MD squared plus MD squared is going to be 2 MD squared. And then they already have a common denominator of 4. So I'm just going to go ahead and rewrite it as 2 MD squared, because 1 plus 1 is 2, and then the denominator is 4, so I'm just going to carry that down. Omega remains on the outside. So once again, I highlighted in this particular problem here, 2 and 4 is going to cancel out to be just 1/2. So I'm just going to go ahead and cross out the 2 and then reduce the 4 to a 2 on the bottom. So it's really just MD squared over 2, and then that's going to be omega on the outside. Okay. So let's go ahead and do this one. Here, I'm just going to pause here because essentially the question is asking you to find L2 in terms of L1. I already have an expression for L1, so I can go ahead and set up L2. So similar process here, except all you have to do is really just pay attention to the distance. The distance from M to M previously is D. Now the distance from M to M is 2D. So I'm just going to say omega 2 is just the sum of these point masses, the moment of inertia times omega. Omega, once again, is kept the same. But here, from axis of rotation to where the mass is just now D, because half of 2 is just 1, so it'd just be D. If you kept up previously, the distance just be D here, but I want to write it out twice because there are 2 masses left and right. And then once you square that, md squared plus md squared is just 2md squared, and you have omega here. So here, essentially, the problem is pretty much done. All you have to do is just kind of outsmart the problem a little bit. I'm just going to go ahead and pull my coefficient on the front. Oh, excuse me. I'm just going to, oh, I could say, just rewriting the 2 in the front here, and then I'm going to put everything else in parentheses and highlight it, because if you look on the left side, for L1, you have md squared omega over 2, right? So here I can just highlight md squared omega, and under L1 I can just solve for md squared omega because these are all constants in this particular problem. The mass is constant, d is constant, and then omega is also constant. So to get md squared omega by itself, I'm just going to multiply both sides by 2. So I'm just going to bring this 2 from the bottom right up to the top left. So I can say that 2L1 is equal to md squared omega. Well, in my work on the right here, I have md squared omega. So all this highlighted in yellow is just going to be 2L1. So that's a true statement from my work in the first setup. Okay. So here 2 times 2 is going to be 4. So therefore we can say that L2 is 4 times L1. And that would be choice B. All right. Let's move on to the next one. Okay. Here's the next one. Here essentially you have a rod that's hinged at point A. You have a bullet that's coming in at some speed V and it's going to strike the end of the rod. And it wants us to find the angular speed of the system immediately after they collide. So this is a conservation angular momentum that allows you to use linear momentum and then cross it by the distance away from the hinge. And then that's going to equal to the system as it rotates afterward. All right, so here is M for the mass, and then the length of the rod, once again, is capital L. I just label it just so I can have a reference here. All right, so essentially this is a conservation angular momentum problem. Li here is going to equal Lf, but you can break it up. Initially, it is the bullet that is moving relative to this distance away from the hinge, which is the length L, which is already perpendicular to the momentum of the object coming in. So here you have a particle M, and it's moving V in the horizontal direction. And the distance away from the hinge is the distance of L. That's already on the y-axis. The momentum is in the x-axis, so that's already perpendicular. So angular momentum is the cross product of linear momentum and the moment of arm relative to the hinge. So here, I can just break up Li into C for the moment of, for the coefficient of the bullet. Okay, and the bullet is treated as a point mass, so C here is going to be 1 later on. All right, other than that, I'm just going to go ahead and break up the right side into the moment of inertia total, because the problem states that the bullet is going to get stuck in it. So the rod is going to move, and then you have a bullet. So you really have two objects moving. So I just put I total, and then omega F is essentially what we're looking for. So here, I'm just going to break up CPR into CMVR. P, linear momentum, is simply the mass of the object that's moving linearly times its velocity. So on the right side, I total is going to be I rod plus the moment of inertia of the bullet. Once again, because there are two objects now being stuck together. Okay. I highlighted C here because C is just 1 for the bullet. We treat it as a point mass. And then R here is capital L because the bullet strikes the rod at the end at point B, which is the distance L that's perpendicular away. So make sure you apply R correctly and make sure it's always perpendicular to the velocity vector. All right, so in this case, that is just a distance of L away from the axis of rotation or the hinge there stated in the problem. The rod has a moment inertia of 1/3 ml square. It's 1/3 because once again it's hinged at the very bottom, not the center. So make sure you use 1/3 versus 1/12, or if the pivot is shifted somewhere else, that's not the end. Make sure you apply the parallaxes theorem. Okay. Here I bullet is just ml square. Once again, the C value for the bullet here is just 1, and then the mass of the bullet, and then how far did it strike the rod. And that is, it strikes at the end at point B, so the distance from the hinge is L, so it would just be ml square. Omega F is on the outside of the bracket. So here, I can just go ahead and really introduce a common denominator. Everything on the left side stays the same, right? The 1 outside, I just got rid of my next work here because you're just multiplying by 1, so it's redundant. On the right side, in parentheses, you have a 1/3. The second term doesn't have a fraction or doesn't have a denominator, so I'm just going to multiply top and bottom by 3 just so I have a common denominator 3. But if you look here, you have a 3 on the bottom, and then you also have an L square on top. These are like terms, so I'm just going to factor that out. Okay, so the numerator, ml square, and then 3ml square has L square, so I can pull that out. And I can just factor out the common denominator on the bottom as 3. So it would be L squared divided by 3, and then I would just rewrite everything that I haven't factored out, which is just M plus 3M, and then omega F once again just gets carried down here. At this point, if you want, you can, or you can keep it as this, but I'm just going to go ahead and I see that there's an L on the left side, and then I see an L square on the right side. So I'm just going to go ahead and cancel the L on the left side with one the square L on the right. And then at the same time, there's a 3 in the bottom here. So I'm just going to multiply both sides by 3, but there's an L at the top on the right. So I'm just going to move to the bottom left because ultimately, right, I'm trying to solve for omega f, so I need to get omega f by itself. Really, here the physics done. We're just manipulating this algebraically. All right. So I want to multiply both sides by 3. That's why there's a 3 in the numerator of my work now. I want to divide both sides by L. That's why there's an L there. And then I'm also going to divide both sides by the stuff in the parentheses, which is capital M plus 3M. And that is left in parentheses there. And that is going to match with choice. Let's see. So you're looking for 3MV, 3 small MV. So that's going to be C. Because on the outside there's L. I have capital M plus 3M. And the answer choice here has it as 3M plus capital M, which is the same. So that is answer choice C. Okay. All right, let's do the last one of this particular video. Here, you're given a torque versus time function, and it says that the moment of inertia of some object is 4 kilogram meters square, and it's already moving at a velocity of plus 0.2 rad per second. So the angular velocity is given, and it experienced some sort of varying torque. Okay, so the torque initially is 2, and then at some point at times equal to 2 seconds, it came to a stop, or not came to a stop, but the torque disappeared. The torque approaches 0. All right. So the initial torque is 2. After 2 seconds, torque changes to 0, and it wants us to find the angular velocity here at 3 seconds. So I'm just gonna do this the easiest way, I think, for this problem, and then I'll show you how to use calculus. So if you're in calc and you're expected to do this using calc, follow along in the next slide. All right. I know that angular impulse, all right, is net torque times change in time. When you apply a torque over a certain amount of time, the object speeds up or slow down. If the object speeds up or slow down, there is some sort of change in angular momentum because omega changes. So I'm just going to say net torque times time equals change in angular momentum, aka impulse. Here, I'm just going to break up change in L into I, change in omega. It's one shape, so the moment inertia is not changing, right? It's the angular speed or angular velocity that's changing here. So you can break up delta L into I times the change in angular velocity. Again, it's asking for the angular velocity at 3 seconds, so I need to find omega f. So I'm just going to go ahead and break this up so I get omega f. Change in omega is just omega f minus omega I. And then I just divide both sides by I, just so I can isolate for omega f. Okay, so if you kept up with the algebra, divide both sides by I, break up change in omega into omega f minus omega I. And as you can see, we almost have omega f by itself here. All you have to do is move this negative omega I to the left side by doing the opposite operation. So you would just add it to the left side of my work. So here, to find omega f, we need we need this particular value, the net torque times time over the moment inertia, which is given as 4 in the wording here, and then omega I, which is given as positive 0.25. Well, how do I find this information, net torque times time? Well, you're given the area of, you're given a graph of torque versus time. So the one thing you can do is find the area of this particular shape from the horizontal up to the line itself. And then the area for this particular graph, this is a torque versus time, is your angular impulse. Okay, so essentially it's your change in L. So I'm just gonna go ahead and find the area here. This is a triangle, so I'm just gonna do 1/2 times base times height. The base is 2 and the height is also 2, so it'd be 1 times 2 times 2, which is just 2. So the area is just 2, so I can just use that area and replace it for net torque times time. So net torque times time in the numerator here, that's just 2 by just looking at the area. The moment inertia is 4, and the initial angular velocity, which is given as positive 0.25. So if you do this, 2 over 4 is 1/2, which is 0.5, and then 0.5 plus another 0.25, which is 0.75. Okay, and that's choice B. Now, again, I think this is the quickest way to do this one, is just by looking at the area of a torque versus time graph and know that is your angular impulse. Using calculus, here's the same problem, but I'm just going to do this using calculus strategy here. Well, you know that net torque equals I alpha. Okay, well, what is the net torque for this function? Well, it's just varying torque. As you can see just from this graph, as I said earlier, at times equal to 0, the torque is 2, and then at times equal to 2, the torque is 0, so it's changing, right? It's not constant. So here I'm just going to apply y equals mx plus b just so I can find the equation of this particular slope. Why? Because it's not constant. So I can just go ahead and do this. I can say torque, which is in the vertical axis, which represents y. The slope here is -1. From left to right, this is a downward slope, so it's negative, and the rise is -2, and run is +2. So -2 divided by +2 is -1. Your independent variable here is t, and then the y-intercept is a +2 because the graph said so. And then instead of saying -1t plus 2, I'm just going to go ahead and get rid of the 1. I'm just going to say it's -t plus 2. So this is your torque function, right? And which makes sense, right? If you plug in times equal to 0, the torque is 2. And if you plug in time as 2, well, -2 plus 2 would just be 0. So make sure you're able to write the equation of, a linear line correctly. So here, now that I know what torque is equal to, I'm just going to substitute it out. So instead of saying net torque, I can say that torque is -t plus 2. On the right side is I alpha. Well, I can substitute I out because I is just 4. Once again, I is given. And then here, as you can see, I have A, or my angular acceleration. So I can just go ahead and solve for angular acceleration here by dividing both sides by 4. So it'd be -t divided by 4, and then 2 over 4 is just 1/2. Well, once you know acceleration here as a function of time, A here is some sort of function of time here because there's a t on the left side, right? It's not constant. Well, if torque is not constant, angular acceleration cannot be constant as well. When acceleration is not constant, you do have to use calculus to find all your v's. So once you know your acceleration, to find the instantaneous angular velocity at any point in time, you would just integrate your acceleration function. So if your linear kinematics is good, you would just use the same skill here, right? So to find v of t, you would integrate a of t with respect to time. So here I'm just going to go ahead and plug in my alpha. Alpha is -t over 4 plus 1/2, which is right here where I'm circling back and forth, right? And then you're going to integrate this with respect to time, of course, because time is your independent variable. I highlight the 2 here because this is important, right? The torque is varying between 0 to 2 seconds because at 2 seconds, the torque gets to 0 and it actually stays 0 for the rest of the graph. Okay, so torque is changing from 0 second to 2 second, which means acceleration is also going to change from 0 second to 2 second. So I'm just going to highlight or circle this 2 here because I think that's important. You don't want to plug in 3 seconds, right? While the graph goes all the way to 3 seconds, the torque is changing up to 2 seconds. So it's important that you plug in the correct time bound here. So if you integrate this correctly, the integral of t over 4 is just the integral of -t over 4 is just -t squared over 8. And then the integral of 1/2 is just 1/2 t because you're just slapping a t. And don't forget your coefficient or your c value here, your constants. Okay, so here I'm just going to plug and check. T is 2 seconds. And then again, it ends at 2 seconds because that's when torque goes to 0 and it stays 0, right? So, and then t here is also 2. So I highlight the values where I plug in 2 for t. And then c here is my initial angular velocity, but the angular velocity is given as 0.2. So really 2 squared is just 4, but the negative sign gets carried down. And then 1/2 times 2 is just a +1. And then I substitute out for omega I for 0.25, which was given. And if you do this, you also get 0.75, and which matches, again, choice B. So anyways, I hope that helps. Stay nerdy. Don't be whack.